講師のSergioさんはインテリジェントロボット、ビジョンシステムとメタファクトリーの開発についてお話しいただきます。では、Sergioさん、お願いします。
Hi everyone, I'm Sergio. I am an engineer from the Robot Manufacturing Unit Department at ITRI. Today, I will talk about our intelligent robot vision systems and meta-factory developments. I'm going to introduce to you two key products developed by our department, which are RobotTwin and FO Vision. Nowadays, in the context of global connectivity, an increased demand for efficiency and an accelerated production pipeline, businesses are making their physical factories to be described entirely in terms of software. No matter where users are located around the world, with the aim of 3D digital environments, virtual reality deployment, and a communication scheme between digital and real assets, users can perform sensitive operations in the digital world and bring optimizations to the real world. This is the idea for MetaFactory, which serves as a realistic virtual environment replicating actual factory layouts, robotic cells, and workpieces. Along with virtual reality interaction, real manufacturing sites can be completely software-defined. As a result, users can navigate all the way through the virtual scene and test sensitive operations safely. More specifically, RobotTwin, as part of MetaFactory, intends to link motion commands between real-world and virtual scene. Users can deploy robot actions back and forth and collect relevant data from the real world to the virtual scene. The purpose of RobotTwin is to achieve capable human-machine cooperation by connecting VR equipment combined with high-fidelity physical engine from NVIDIA Omniverse, resulting in a human-machine mixed interactive simulation technology. Here we have one video. For instance, the user is wearing a VR headset and also grabbing a virtual stick. Using one of the VR controllers, making the virtual world follow the stick. This action is related to robot teaching. In another case, we have a user wearing a VR headset. Meanwhile, the virtual robot is performing defined motion commands and compounds of data coming from the real world in the form of images, and other graphics are projected into the virtual environment for the user's interest. RobotTwin comes with two operation modes. The first one is known as follow target mode. In this mode, the user grabs the virtual stick and the virtual robot will follow this tool in real time. Therefore, joint states will be shared to the real robot, resulting in real-time synchronization. Robot safety is also considered as well, along with a virtual reset option to prevent both robots from any undesired displacement. One more feature here is that 3D animations of the workers are included in the virtual scene to make the virtual reality experience more realistic. Let us now refer to RobotTwin's second mode, known as play mode. In this mode, virtual robot is given defined motion commands. Those are shared to the real robot to achieve real-time synchronization. At some point, data from the real robot is collected and projected into the virtual robot. This is all part of a loop to simulate a running production line. So now let us proceed with our second product known as FO Vision. FO Vision mainly consists of three pieces of hardware, which are a 3D camera, a particular lighting source, and an edge computing device. The system will collect light-controlled 2D images along with 3D point cloud data to be processed by an embedded AI object recognition model. At the same time, the system will compute pickable points over the work pieces, and it will command the robot arm with inverse kinematics to perform pick and place operations. As a matter of fact, AI training for object recognition demands reasonable training datasets. Therefore, manual labeling can be tedious and time-consuming. In contrast, FO Vision offers a modeling and automated AI tool capable of mapping real-world 2D images into their work-based 3D CAD model representation. This tool not only enhances the realism of the virtual environment, but also automates the generation of annotated datasets, capturing pickable and unpickable points for each workpiece. To ensure that valid training dataset acquisition is doable, the AI annotation tool makes use of our domain randomization approach. In this way, several parameters will vary, such as workpiece posture and quantity, camera lighting and posture, light intensity and color rendering as well. So here we can observe how the algorithm makes the change in the beam color, and also the objects are placed randomly, and they all have variations which will make the training dataset stronger. So with all this being said, let us observe FO Vision deployment. Considering a real working environment, FO Vision collects data from a container loaded with metallic pipes and commands an industrial robot arm. The synthetic training dataset generated to train the embedded AI object recognition model proves to be valid in this case. So here we observe the objects loaded into the container, and then we can see the masks obtained by the AI object recognition model. And all of this is the result of the trained dataset, which has the variations mentioned before. So this is all for my presentation, and thank you for your attention.
Sergio さん、技術を分かりやすくご説明いただきありがとうございます。それでは Q&A 時間に入ります。Question 1. Do you consider safety for roboting?
Hi, thank you for this question. Yes, of course, we have included safety for this application. We can set up safety limits in the robot controller itself, and at the same time, we have included some programming functions in our virtual world application. So both real robot and virtual robot will stop if the user is pressing a button on the application. And we have also set some safety limits in the virtual world as well. So all is covered in terms of safety.
はい、もちろんです。ロボットが特定の空間から出ていくのを防ぐため、ロボットに安全制限を設定し、バックエンドもいくつかの安全機能も追加してすることで、ロボットが特定のスペースから動かないようにしています。実際のロボットおよび 仮想ロボットも停止命令できます。さて、次の質問です。How to set up robot train?
Oh, thank you for this question also. For this question, let me refer that we also follow the instructions given from the VR set maker, and at the same time, we connect the robot to the PC by TCP/IP protocol. So this is quite a straightforward action. You will find it quite accessible to set up the system if you follow our example, which is using the UR10 robot and this HTC headset. In general, it is very easy setup, and if you really need to ask questions, we are always ready to help you.
具体的な例を挙げますと、ユーザーはメーカーから提供される VR セットのセットアップ手順に従って、ロボットを PC ホストとインターネットを通信で接続する必要があります。一般的にセットアップは非常に簡単です。そろそろお時間も迫ってまいりましたので、その他のご質問は別途にてメール回答させていただきます。